Okay, today we want to continue our discussion about convex optimization. Let's do the fast review of the materials of last meeting. In the last meeting we talked about the basic properties of and some samples. We talked about the operation that preserve the convexity. Today we will continue talking about these operations, and we will go through the conjugate function and quasi-functions and log-concave and log-convex functions. Okay. Okay. Let's review some definitions. In the start of this chapter, we talked about the definition of the convex function. We had before the definition of the convex set, and here we define average the point here. It's theta x plus 1 minus theta y. If it's this one is less than the value of theta f x plus 1 minus theta x1, we call the function is convex. This part here, part 1, it shows the value of the function in the points between x and y. It means this red area, and theta f x plus 1 minus theta y is this line. And if function is concave, the minus f is convex, and so on. Then we review some examples and start talking about the we had a discussion in the previous meeting about the extended value extension. We said if the function only defined in the sum domain x, we can define the x hat which has a value plus infinity, where the x is not in the domain of the f of x, and we use oh my god, yes, we use these properties for the operation that preserve the convexity. Then we went through the first order condition, and we talked about that value that always the convex function f here is in the one side, in the up level of this function, and we call this line as a support of the function in the point of the x. And the second order condition that we said, if it's bigger than equal to 0, or if it's the matrix is supposed to be positive semi-definite, then the function will be convex. We had some example. Here we use the second order condition to prove that this function is convex. We use same proof for this perspective, this function, this perspective function, that we find that if y is bigger than 0, the function is convex. We talked about the epigraph and sublevel sets. Epigraph, as you can see in this picture, it's if this line, this function here is f, the area that it has a shadow here is the epigraph of function f. It's if the f is a convex, the epigraph is a convex set, and it's one way that you can prove the function is convex or not. Then we review the Jensen inequality in the basic and in the extension part. For the extension, we talked about the expected value of the function, and we talked in the discrete, if you have a discrete domain, what is the Jensen equality. After that, we start to talking about the operation that preserve convexity. The first we talked about the three ways that you can prove one function is convex or not. First one is using the original definition that says f of theta x plus 1 minus theta y is less than equal to the theta f of x plus 1 minus theta f of y. The second one is using the first order and second order condition for proving that the function is convex or not. And in the third way, we can use some decompose one complex function to some operation that preserve the convexity, and based on that we can say one function is convex or not. We talked about non-negative weight sum, decomposing with the affine function, and pointwise maximization, pointwise maximum and supremum, and we talked about the decomposition. I will review very fast the material that we talked. Okay. First one was positive weighted and sum. If we have a summation of the some function, some affine function, the result of the function, the result function is convex. For example, you can see here the barrier function that we talked about that. Then we talked about the piecewise maximum. If we have a function f1 to fm that they are convex, the maximum of those functions it's a convex. The original function that's for example piecewise linear function, something like f of x that is max of some linear or affine function is convex, or some of the largest component of the x in Rn, which is not easily, you cannot find a closed form equation for that. It's really hard if it's the size of the n is bigger than 5 or 6. And the function of f x and y is convex if in x for each y in a we have this g of x, which is the maximum of the f of x and y. We have the same thing for the minimum. We reviewed that for the maximum we don't have any condition over a here, but if we have a minimum we have to have a as a convex set. I can write it down some of the some example of how this one works. For example, if we have a okay, if we have f of x f of theta x plus 1 minus theta y, we define here is as a maximum of bunch of function f1 of theta x plus 1 minus theta y, f2 of theta x plus 1 minus theta y, as if f1 and f2 are convex, we have based on the definition that the maximum of theta f1x plus 1 minus theta f1y equals theta f2x plus 1 minus theta f2y, and this is less than equal to theta max of f1x and f2x plus plus 1 minus theta max of f1 y plus virgule f2 y, and this one is equal to theta of f of x plus 1 minus theta y. It was some proof for this one, and then we talk about the decomposition. If you remember, we had composition, sorry. We talked about the composition. If we have a function f of x, which is h of g of x, we talked about how we can, based on the condition that we have on the g and h, how we can say the function f of x is convex or concave. First, we calculate the first derivative, f prime of x is equal to h prime of g of x, and if we do the second derivative, we reach to the if we get second derivative, we have h second s double prime of g and g prime square plus h prime g double prime, and based on this there is a two term here. Let's call this one number 1 and this two number 2. As you can see here, this part is always positive, and for having a convex function we need to have this one is bigger than equal to 0. Therefore, if we want to have a function, this one is always positive, and if h double prime is positive, it means the h is convex, and if this one is negative, it means it's concave. And for here we have the h prime. H prime means the slope of the function, and here we had h tilde, that is the extended value of the function that I mentioned before, and g double prime here, it's convexity. It's talking about the convexity of the g. If this one is it's a positive value, it means the g is convex. Therefore, for any f, if we want to find the f is concave or convex, we can set a function that can satisfy the condition. For example, if we want to have a f is a for example, if we want to have f is a concave function. We can play with each of the variables here. For example, if we want to have the f is concave, this value is supposed to be less than equal to 0. Therefore, with this positive term, we need some function that is concave here. Therefore, h can be concave. And here we have two options. We can have one concave function, which means the g double prime is negative, and some increasing function, which make this one positive. Or we can have some convex function and and some decreasing function. Let's write it down. This one, g can be concave. If this one concave, it's this one. Therefore, h supposed to be positive. It means non-decreasing. And we have, this is a number 1 here, and number 2. G can be convex, and H non non-increasing. Okay, and we have some example here. The exponential of the g of x, the exponential is it's a convex function, and if the g is convex, and the exponential is non-decreasing, therefore this one is non-decreasing. It means this part is positive, and if the g of x is positive, this term is positive. H of x, it means exponential itself is convex. Therefore, the function that has the exponential of g of x, if g of x is convex, will be the convex. And we can have a different function. For example, we can have, we can have h of x is equal to I don't know, some, I think we had enough examples in the last lecture, and let's go to the vector decomposition. Yes, composition, sorry, vector composition. In here, In the previous case, we had only the input of the h. It was it has one input, but here we have a bunch of input. They are a vector of the g's, and we have the same condition here. If we do the matrix derivation of the derivative of the f of x, we have this term here. Again, we have a we have some quadratic form of the g prime of the x, and here we have g double prime, and again, if we can do the same argument about the scalar case. Here, if the function, the extended value of h in each of the argument is non-decreasing and h is convex, for gi's that are convex, we can have the function that is convex. Here, in each argument, non-decreasing means if we fix all of the argument except one, and if we change the one of the argument, the value, for example, be non-decreasing or non-increasing. Yes. Okay. And the example here is the sigma of log of gix, which is convex if gi's are concave and positive. Because first we cannot define the g for the negative value, and if g is convex, the summation of is concave, the summation will be concave. If you remember in the review of the this chapter, I said that for the finding the for maximizing a function, if it's jointly convex on x and y, for maximization we don't have any extra condition. But here, for finding infimum or minimum of a function, the c, which is the domain of the y, it's supposed to be a convex function. Then the function g is convex. As an example, for example, if we define f of x and y as this one, and we have these two conditions here, minimizing over y, it means we find the minimum of this function, which lead to this term, and we know from the convexity this is a quadratic term, and for having this function positive we need to have this value, this matrix, positive semi-definite. And there is there is a function, distance function, which find the minimum value of this norm x minus y in the some convex set S. This one is a convex function. It means if we have some convex set, something like this, this function is this green function, and this one is a convex. The other thing is perspective. If we have a function from Rn to R, we can define a function g which has a one dimension more than the f as input and map to the R. We can define this function as t of f of x over t, which domain of the g is the point that x over t is in domain of the f and t are positive because it's x over t, and this one is convex if the f is convex. As example here, if we have a function f of x, we know this function is quadratic term and this function is convex. We can define a g of x t which is equal to t x transpose t multiple x t, which this one is equal to this term here because you can cancel one of the t's, and based on that f of x is convex, and we know if we define some function something like this, t f of x over t, this preserves the convexity. Therefore this new function g of x and t is a convex function, and we know that f of x, that is negative entropy, it's negative logarithm function f of x is convex, and we can do the same thing as we did here. We can define the new function g as let's write it here, g of x t is equal to t minus log of x over t, and if you extend this function, it's here we have log x minus log t, and we have minus sign here, therefore it's minus, and this one is plus, and we multiply by t here and here, and we have this term here which is convex for in the R plus, and we can do the same for a function convex of f of x. Here we know this function is convex, and we define t equal to c transpose x plus d, and this one is equal to t f of something divided by t, and it's same as the previous one. This one is convex, but here we have a condition that this one is supposed to be positive. The next one is the conjugate function of the convex function. We define the conjugate of a function f as this one. It means the maximum of the y transpose y minus f of x, where the x's are in the domain of the f, and this function here is convex, even f is not convex. It's we have a conjugate in the complex number, but this one is little different. Here we have a function f of x, and we have this line x and y, and for the point here, the value that we can find for minus f of x is this point, and we can change the slope of the line. If we change the slope and and reduce it, we can have some line, something like this, and you can see here the value will be going up till the point that this point and this point. This is the maximum value that the conjugate can have. After that, again, this one start to coming down. If we have the conjugate of the f is not the same as f, it's create some function like this one, and conjugate of some function is not equal to the same function. We will use it later in the and this topic for optimization. For the next meeting, we will talk about the some optimization problem, and we will use these definitions. Let's do some examples and see how we can find a conjugate of how we can find the conjugate of some given function. Let's start with this one. We have negative logarithm. F of x is equal to minus 1 log of x, and the conjugate of f as a definition is equal to supremum or maximum of x, xy plus log x. And for finding the maximum of this one, we can use the derivation of the function here. because we want to find the a maximum of this function. Therefore we can get a derivation of this one. This one is create only y, and plus the for the log of x we have 1 over x, which is supposed to be equal to 0. Therefore from here we have x equal to 1 minus y, and we know this one is the point that we can have the maximum. And for finding the maximum of this value, we can replace the x by 1 over y, and in the original function it's f conjugate of y is equal to, instead of x we have 1 minus 1 y multiple y plus log of minus 1 over y, which this one is minus 1. And for this one we can flip this one, and we have minus log of minus y. Okay, from here we have a function, and if you get a derivation of this one for the for example, if I call it let's call it h prime x is equal to the thing, this is the round h round x, and this is the h. Okay, and this is the log we have only for positive numbers. If y is negative, we have this function, and the shape of the minus log, the log is this is 1, and this is the log, and minus log is this function. And you can see here in this area we can find the maximum value of the function, but we don't have anything here. Therefore, for having the maximum here is plus infinity to keep all of the function to be more than the value of the function, and we can use the extended value function for this part. And for the part that it's less than 0, less than equal to 0, we have plus infinity, which is the maximum, because here is goes to the plus infinity. Okay. And we have a strictly convex quadratic form, something like this, and we can find the conjugate function of this function, which is the maximum of x y transpose x minus 1 over 2 x transpose qx. And if we do the same procedure that I said here, if you want, for example, we can get a derivation of this one, and it's suppose where it's transpose, because this is matrix. matrix. Yeah, you can do the same procedure and find the conjugate of the function. And one important thing that maybe is useful later, f of x plus f conjugate of x is always bigger than equal to x transpose y. I think it can help sometimes for solving the problems. Okay, next topic is quasi-convex functions. As you can see here, if we have f from Rn to R is quasi-convex if the domain of the f and the sublevel sets S alpha are convex. It means if we draw a line here, the area here in the domain, if this set A to B is convex, the function is quasi-convex, and f is quasi-concave if minus f is quasi-convex. Okay, and you can see here if we move the line up or down, if we move it up, it goes from this side to infinity, but still we have here a convex set. If we move it down, it's this one be smaller, but still we have a convex.
So you that the quasi-convex is that if you have a function that is just part of it, you just care about the part of it that is convex.
No. This function,
is not convex.
Yeah, the function itself is not convex, but if you define a sublevel set in alpha, beta, or any value in that sublevel, the domain of the function, it's convex. It means you don't have something like this. If you have some function something like this, and you define here alpha, yes, here is the set of the alpha, but if I have a here the set here is this one and this one, and in the first couple of meetings we discussed that this one is not convex. Therefore, this function is not a quasi-convex and not concave. Okay, and we call a function is quasi-linear if it's concave and is convex. It means the function or negative sign of the function both of them are convex. Therefore, we call it quasi-linear. I think I have in the. I will. Let me see. I think. Yes. Let's start with the first one. The first one is square root of norm of x, which is this function.
Convex or concave, you have to draw the just plot it, or
No.
can we do it without plotting?
Yes. Okay. This function, if you define some sub level set here, the domain is always convex. Ceiling function, it's quasi-linear. It means the value of the function, it's this function and the minus sign of this function both are quasi-convex. Therefore, this one is the quasi-linear.
Can you say that if you have the convex function, that was
if you have a convex function, I need to think about that. But if you have a convex function, you have the quasi-convex function. But the reverse is not true. You may have the quasi-convex on the R, but the function is not convex. But it will help you when you want to find a minimum or maximum of the function, depend on your case. If you have a quasi-convex function, you can, even the function is not convex, you can find a global optimum of the function. And the log of x is one of the function that is quasi-linear in R+. It means the function and the minus side of the function, they are quasi-convex. And I think these are some examples here, and okay, let me make it here a little faster. Modify Jensen inequality for the quasi-convex function. Here is a little different. In the original Jensen inequality, we had the function, if we had let's see, if we have this function and we define x and f of x and y f of y, and this value of function here, some point in the here, it was always smaller than theta f of x plus 1 minus theta f of y. It means this value here is less than this line here. But for Quasiconvex function, it's a little different. If we have a function here which is something like this. Inequality says the value of, for example, this point and this point on the function is less than equal to maximum of f of x and f of y. This point, if we define it as same as that one, as x and f of x, and this one as y and f of y, the maximum means this line, this dot line, that the value of function is less than this value. Okay, and if and we have a first order condition again for the differentiable f. If its function is quasi-convex, and the value of f of y is less than the value of f of x, the line that we have here, this line, which this is the first order derivation of the f, shows that the minimum is in the other direction of this arrow, and it will help us to divide the search space in two parts, and we can start to searching in the other parts. Okay, I think this is the last topic that I want to talk today, and next week I will go through some optimization problem. We finished the introduction about the sets and convex set and convex function with this last topic. We call it a function log-concave or log-convex if we have this condition. For here, always, not always, but most of the time, we're talking about the log-concave instead of log-convex. And here said, if we have a function f that is concave, the value of f of x in the power of theta multiple the f of y, the power of minus theta, is less than the value of the function in the points between x and y. If you do the log, it's can be the theta log of f of x plus 1 minus theta of f of y, and this side we will have the log f of theta x plus 1 minus theta y, and it's the yes, and we have some famous functions that they are log-concave or log-convex. For example, power x power a on r plus is a convex, and if a is negative is concave. Sorry, if a is negative is convex, and if a is positive is concave. And here we have a distribution, normal distribution. It's the one of the function that if you do the log test on that, it's a log-concave and cumulative Gaussian distribution. The Gaussian distribution is something like this, and cumulative is and if we calculate the value of the log for here, which is close to 1, the value will be 0, and here goes to the infinity. I think it's something like this, but it's concave. The function is concave, and I think I'm done with the there's some properties of the concave that I prefer to keep it for the next one, and for the next meeting I will again review the last topic, that is log-concave with the properties, and start the optimization problems. Any question? Last page. You mean this page?